carbon monoxide and NO. Indium oxide particles are only sensitive to carbon monoxide, and zinc oxide particles are only sensitive to NO. So depositing these three types of particles on the same sensor, you can detect what is the gas and what is the percentage of gas based on there is 3 different or 4 different responses. This is our proposal, and we are working on developing this next generation sensor. What we are expecting is this sensor will have high sensitivity because of the size, nanoparticle size. It has high selectivity because we're using 3 or 4 materials in the same sensor, and it will have very high stability because you're not using a continuous wire or continuous bulk material, which is susceptible to degradation, cracks, and so on after longer durations. This is consisting of isolated particles deposited in that. Thank you.
I have one clarification and one question. Clarification is like when you are seeding to the DMA, the charge particle, what you are measuring is electrical mobility diameter. But what probably you are showing through 10 images are geometric diameter. So there is some...
Both are different. But the pressure mobility analyzer is used to control the process. So we know after you optimize it, you know if this is your mobility diameter, this is the geometric size you get.
So you are interested in like what geometric size you are doing?
Finally, we are interested in the geometric size. The DMA is used to control. Okay, so maybe you are in the beginning you are saying your mobility diameter is, in fact it is called electrical mobility equivalent diameter. Okay, it is 20 nanometer. But the geometric dimensions are totally different.
Okay. So
but they are proportional.
Now coming to my question is like you propose tin oxide and indium oxide. How specific they are to the specific gases that you say?
That's what I said. So it all depends on the chemical reaction which will take place.
Because in ambient there will be many gases which might have like overlapping specificity.
Yeah, so that is what you can, this is the method to do is that you can't work with one sensor, because this is a problem with oxide sensor, exactly what you are talking. Because for example, tin oxide, it responds to most of the reducing gas is similar, and its response to oxidizing gas is similar. Okay, it cannot differentiate, but its sensitivity is different. It's very sensitive to some gas, like its electrical resistance will increase in 4 gases. But in one gas, it will increase, resistance increases very high, in other gas resistance increases low. You can improve this sensitivity by modifying it. There are chemistry. What has to be done is chemistry at the interface has to be modified.
But the results are fascinating, so congratulations.
So, how about...
Just one clarification. When you charge the nanoparticles, and when they go from, say, graphite to palladium, don't they touch each other because they are energetic? They have energy.
No. I think my suspicion is that you are mixing 2 or 3 things. Say your question again.
When you charge a nanoparticle, because you said
In the DMA.
And then they go to the graphite base, which you showed.
Sure.
And you say that all the nanoparticles don't touch each other. Yes. So when they are because when you charge, they are energetic. They have energy. So can't they touch each other? When
They will touch each other if you deposit too much. You have to control it.
How do you ensure that?
Because that is the good thing in this process is I can show you, primitively I can show you that because the nanoparticles are being prepared in the gas phase, okay, typically I will show you. If they are prepared in the gas phase and you can see that, yes. So what you have is a condensation particle counter. You can count the particles. Now we know how many particles are passing this line per second. This is not because you can take a sample of this gas into the condensation particle counter, and the condensation particle counter, what happens is these particles, there is another volatile liquid which condenses on this particle, the particle becomes bigger, so that you can count with light scattering, like this method.
We know
you know the number. You know the number, and so you control the time, and you know how much time, how many particles are deposited. So you have to control that.
Are these particles of same charge?
That's a very interesting question. The process works on this assumption that all the particles have to be same charge. Otherwise, two particles having different charges and different mobility will be selected.
Yeah.
Okay? So this is how the charging process has to be optimized. The good thing is in the charging process, 99.9% of the particles have the same charge.
Same charge. So they are repulsive.
They're repulsive. They're the same charge. No. Same charge means, I'm sorry. They're two different things. Same charge, do you mean positive and negative?
Yeah.
No, they are both positive and negative. 50% of the particles are positive, 50% of the particles are negative because charge cannot come from outside. You're charging, if just the same electron goes to the other particle making negative. So, I'm sorry, so the charging process is called bipolar charging.
Okay.
This same charge means I meant +1 and +2 and +3.
Ah.
That should not be there because if you have some charges which are +1 and other particles have +2 charge, you will do a mistake.
Ah.
Okay? That should not be there. So 99% of the particles have +1 or -1.
So it will be chaos situation.
So some of the particles you are rejecting. This is a complete this process. I tell the student this is like our joint entrance examination works. You are preparing so many, and out of that you are selecting what you 20 nanometer only, and you are throwing others are being rejected. So we don't care about the yield at this stage because it's a laboratory scale, and we want to have good control on the size and not bothered about that. You have to throw the particles out.
So that means the particular size range 10 to 20 or 30 to 40 you have shown. That is the only range that is more effective or more sensitive than other ranges.
As smaller the size is, the better is from this. But too much small is not good.
Okay.
Yeah. So 5 to 35 nanometer, this is a good thing. I would say.
Okay.
And first, I'm very happy that I was considering myself to be fortunate.
Sir, after some time, like temperature is increasing or decreasing, and humidity is increasing or decreasing,
Sure.
maybe the sensitivity of the sensor will be reduced
Sure,
or increased.
definitely.
How will come to know that the sensitivity of the
This is always, this is what has to be done. Calibration and all those things have to be done. So because sensor gets, especially all the gas sensor, they get affected by anything which will happen, chemical or physical reaction which will modify the surface. So one has to understand, maybe maybe somebody should have a humidity sensor also along with it, and so that you can modify or you can calibrate so that you have a set, you also know what is the sensor, what is the humidity at that point.
You said calibration is needed.
Calibration is This sensor was working at room, that was the good thing. This sensor was working at room temperature, and that's how you can also control it, that many of those humidity problems are there when temperatures are high.
कहाँ नहीं हो रहा है क्या खोल के देख बैटरी दिखाता नवेश भाई
friends, good evening. My name is Amandeep Dubey and I'm a business consultant and I'm also a product developer. I'm the developer for what is known as the Envirotech Live platform. It is India's first real-time web-based data reporting interface that we created about 6 years back, which is currently enabling industries, instrument suppliers and regulators to connect their analyzers of all types, right from analog to digital, to this platform and also be able to manage their data in real time. So that's an application that I have been running for the last 5-6 years. We have 200 plus industries on board with us, and we have created for the industry and the regulators and instrument suppliers a platform on which they can not only manage data but also use that as a knowledge repository. So if something goes wrong somewhere, how do I consolidate the intelligence around it? So there was a storm, I want to record that. So we have built facilities like this in this kind of a platform. We've constantly heard what our customers, industries and regulators are saying, and that's our modus operandi for any kind of product development that we undertake, that we listen to the customer and we keep